So, welcome to lecture 30 of NCS 472. In this lecture, we return from spring break and from a week of project presentations. And we were smack in the middle of chapter 10, so there is some recalling to do. So, I will explain how filters work, and we will analyze the gain and the shift, uh, proving the continuous version of a theorem we encountered earlier in the course when we were studying discrete signals. So this leads to the Bode plot, and this will be illustrated on a circuit. So electric circuits are used to realize filters. We will see a peak filter. Um, then in this chapter 10, we will on frequency domain methods. We consider then feedback, and we design feedback in the frequency domain. So this will be explained with an example of a credit card balance, which if no payments are made, the balance grows exponentially, grows out of control. Okay, what are we looking at? We are looking at filters, but in a more general way, we're looking at also mechanisms and circuits. So we use the more general term a plant. One could also use process, but plant is the term that is used. So we consider linear, time invariant, and causal maps. And a plant is maps one input signal into an output signal. So if we think about information processing, then we would speak about filters. If we think about a mechanical process, then we have a mechanism. And the third category of plants are the electric circuits. So linearity means that the linear combination of the input, if we know the output for the output of a linear combination is the linear combination of the outputs of the components in the input signal. The causality means that you cannot make something from nothing, and the plant doesn't change over time. So there is no the definition of the plant does not change, and by these three properties we can characterize a signal entirely by the response of the unit impulse. So in discrete time, this means we have the signal 1 0 0 0 0, and that has a very natural continuous analog. Okay, so we have this star operator, which was computed by a convolution of just think about multiplying two polynomials together. So that's computing the coefficients of the product of two polynomials is actually computing a convolution. In this part of the course, we consider continuous functions, and this discrete convolution operator has a natural extension. And that's the second definition that we have encountered earlier. Okay, so that's the setup. Here is an exercise. We did similar exercises on discrete signals. So here look at the output defined by taking the input, but then at time halved, and show that this filter is linear, causal, and time invariant. So the main purpose of this exercise is that you recall the formal definitions of these three important properties. So that's what is meant to justify your answer. Just giving yes or no will not give you credit for this exercise. Okay, then we design our filters and our feedback in the frequency domain. So with the Laplace transform, we take any function of time for which it makes sense to integrate, so it's integrable, and we compute the Laplace transform as the outcome of this integral. Okay, so that means that what we have countered earlier, so the convolution product is then corresponds then to the ordinary multiplication of the Laplace transforms. So we have the impulse, the unit impulse, that is also a function in time, and that is then described by its Laplace transform. The little h is the response of the unit impulse. The capital letters are the transformed. So we go from the time domain to the frequency domain, and we've noted earlier that we can interpret this S as also an operator, as kind of the inverse of the integral. It's kind of a formal derivative operator. We will encounter that later. So here we have the notion of the transfer function of the filter, which is the continuous analog to the Z transforms we considered with discrete signals. Okay, so now is our first result. What determines now essentially the behavior of a filter? Well, we take the response to a sine function running at various frequencies, and we look at the output. Then for a linear time invariant and causal filter, we have that the transfer function determines the amplitude gain. So the transfer function then evaluated at the omega multiplied by the imaginary unit, and there is also a phase shift that uses then the angle. So every complex number has a polar representation. So we have the magnitude, how far is the number from the origin, and then there is the angle with respect to the real axis. So we are using the polar representation when we evaluate the transfer function. Okay, so we are mathematicians, so we are using the convention that the little I is the imaginary unit. Alternative notations are the little j if we go to the electrical engineering or in Python, or the capital I is also an alternative. Okay, why do we work with complex numbers? Well, complex numbers, you can also get it from the Laplace transform, where we have this exponential, and remember from the, or don't remember, but I want to point out that with the discrete Fourier transform, we were working with the roots of unity. We do something very similar here. It's the sine function actually then occurs very naturally, as is explained here on this slide. So what does this mean is that we can write a sine function So that's actually now the bottom line and the main important point of the slide. Why do we use these exponentials, these complex exponentials? Well, the sine function can be written as a linear combination of these exponentials. So it suffices that we know the response of this complex exponential. And we will then know the behavior by doing the linear combinations. Okay, so that's the first step. Now let's look at the response of such an exponential, which is computed by taking the convolution operator, so the continuous convolution operator that we worked on, that we defined at the very beginning on the first slides. So what you see here is that we can move out one part, so actually we get an exponential that comes in, that comes out, an exponential comes in, an exponential goes out, and then we rewrite our integral to get a Laplace transform in there. So we want to write the solution, the output signal, in function of the transfer function of the filter. And here you see that we succeed in getting the Laplace transform in there by replacing the t by infinity. So in some sense we take a limit. So we look at the long-term behavior of this filter. So then we can say that there is a portion that comes smaller and smaller. So what we subtract becomes more and more irrelevant. So in the limit it becomes 0. But remains, or what is most important, is the transfer function evaluated at the omega multiplied by the imaginary unit. So here you see how the theorem is actually already almost there. But we have it now only for the exponential. Remember from the previous slide, so here it is again, the previous slide, that we can write the sine function as a linear combination of two exponentials. So that's the third step in the proof. We know we have derived the output of the exponential. Now we do this with the minus, using the fact that the linear combination, so we have the I times omega, and then we have the minus I times omega. Okay, so we have then the output signal written, although it's not really as the form that we need for the theorem. Well, we need the polar representation of the output. So we evaluate the transfer function at these imaginary units times the omega. We call in the polar representation, we have the radius and we have the angle, so the r and the phi. And you see that the r and the phi, we can go back then to the sine function. So we recognize when we use the polar representation that we recognize a sine function in there. So the recipe is on the slide top right here. Here you see we apply this property then backwards. We read this property here from right to left when we write down the outcome, the statement of the theorem essentially. So to recap, what this theorem says is that in an linear time invariant causal filter, there is the output is always characterized by a radius that depends on the magnitude of this transfer function evaluated at omega times I, and there is a phase shift that comes also from the polar representation. Okay, we will see in a minute what we can do with this theorem. Let me illustrate this with an application. So let's look at the realization of a filter by means of circuits. So this is the lecture 26. So from the 2 weeks ago, for more than 2 weeks ago. So when we look at circuits, we can build networks of circuits by either composing the main building blocks in parallel. So this is where we have the first drawing here. That's a parallel, two circuits in parallel, or we can do them in series. So there is this grounding here that ensures that at time 0 the input signal is also 0. And then we had this useful network, which I still left as an exercise to show that the transfer function equals this. So we have the expressions for making the transfer functions using the transfer functions for the components. So the capital letters Z can be complicated circuits themselves. So we can make new transfer functions. So here the transfer functions are written as y over u, which follows from the terminology that we introduced with the transfer function, the capital H. Okay, so let's look at an example. So here is what they call a parallel resonant circuit. So we have three basic components. We have a resistor, an inductor, and a capacitor. So we're using all three of these elementary building blocks. We have introduced these three basic components along with their transfer functions. So you see the S coming in there, same S as the S that we use in the Laplace transform. So this is a combination of using for the transfer function that network that was the third position on the previous slide. And then we have the parallel positioning of the inductor and the capacitor. So the Z1 is just the resistance, the resistor, but you see that the Z2 is obtained by applying the recipe for the transfer function of two circuits in parallel. So that is this Z2 here. And then let's do some basic algebraic manipulation, which we can do simply by hand. No computer algebra is needed here. So that gives us then a form for the transfer function. And I will use the transfer function. So the form in which the transfer function is written is so that it then translates into an ordinary differential equation. So you see that this circuit has essentially two parameters, the 1 over RC and the 1 over LC. And there is a standard recipe to write the transfer function into an ordinary differential equation. So we will not explore this further here, but in the chapter on differential equations, we described the workings of circuits via the ordinary differential equations. So here in this case, this is a second order differential equation, and we made an analysis of such second order differential equation when we considered harmonic motion. So in a way, at the bottom line here we have a second order differential equation, but you could see this here also as a mass spring system, or the example we then looked at was the car suspension mechanism. And what happens if there is a bump in the road? What is the behavior of the displacement in function of time? So I hope one can appreciate at this point the general formalism for the general terminology of a plant. Whether this is an electric circuit, whether there is a filter, or whether it is a car suspension mechanism, they are all governed by the same type of second order ordinary differential equation. Okay, here is an exercise before we get into Bode plots. So the previous filter was uh, using in the capacitor and the inductor were placed in parallel. What happens if you put them in series? So the exercise is for you to apply the recipes to derive the transfer function for the circuit, and then also to write the corresponding differential equation. So you will also end up with a second order differential equation. Okay, so let's now look at a concrete example. So we had this transfer function of the filter. And what does this filter now do? That's the question. So we have the theorem. So this theorem that tells us what is the amplitude gain of this filter, and then also tells us what is the phase shift. So since this is a numerical example, let's take the two parameters, RC and the LC. So these are the characteristics for the resistor, capacitor, and the inductor. These are the proportions. There is a Jupyter notebook that will be posted, or that is posted by now, if you watch this lecture. So we have the parameters. So this slide summarizes all the instructions. So if the slides are enough for you, then actually the slides are in some sense self-contained in this sense. Here we have the instructions to define the transfer function. Here for ease, I define the capital letter I as the imaginary unit. So this is Julia code, by the way. We evaluate the transfer function at a range of omegas. So I'm looking at the maximal value for omega as 6. So this is where if you would think about what this means, so we are looking at frequencies that are less than 1. So because this omega is 2 times pi times n. And here is then the Bode plot. You see that what this filter does, it for one particular frequency, and that's the frequency half, the filter will give you a peak, will actually only retain that signal. So it's called a peak filter. It zooms in at one filter, at one particular frequency. Only that frequency kind of survives the filter. The opposite, look at the other. So this is an alternative transfer function. So make also the Bode plot. Also try to interpret what this then actually does. So there is the peak filter, but there is also the filter that suppresses one particular signal. And we have seen low pass, band pass, high pass filters. So that suffices that we have only one example. We have seen already many examples of filters. Okay, so let's now look into feedback. So what is it actually that feedback does? Feedback tries to when we look at an unstable uh, process, or we look at a plant that is not bounded. So here we have a bounded input, but the output actually grows unbounded. Actually, it grows exponentially. And you can see this very quickly. Well, you probably know this. The way we see this very quickly, you don't need a transfer function. You know this from real life, but you can see that the pole of the denominator is actually positive. The interest rate is positive. So that means that we have exponential growth. So, and with the differential equations that we covered in chapter 9, we describe this process or this plant as via an exponential function. So this actually counts as almost the prototype definition for the exponential function. This exponential function, you have that the rate of change is proportional to the magnitude. So if the process is growing, then actually the rate of change grows at the same rate, so grows exponentially. So we can formalize this with the operator notation, and you can see by getting to the S here, we replace the capital D for the derivative operator by the S. So the S in the Laplace transform can be interpreted as a generalized derivative or an operational method to look at, to consider algebraic versions of differential equations. Okay, we can represent the evolution of the credit card balance by a plant. So this is now an open loop. Feedback is used to stabilize plant, so it is unstable for all positive interest rates. Okay, so how does feedback now work? So we consider the literal meaning of the word. We take the output and we feed it back to the input. So the diagram makes this kind of clear. Typically this is phrased as a correction. So you take the output and you correct it. So there is this negative to the positive. So there is this correction term that is made by taking the output and feeding it back to the input. So that gives then a closed loop system with the transfer function expressed here as this rational form here. Why is that? Well, here you see the input to the controlled plant. Now we have the original input and minus the correction term. So we then feed this input to the plant. So the should have pointed this out on the previous slide. So the transfer function of the open loop system is P of S. So we have P of S. We factor out the Y. That's why in the denominator we see a plus. So we have 1 plus P times H. And that's the denominator of the transfer function. So we have the transfer function of the closed loop system. And that's what we're looking at to stabilize a plant. Because what we want is that the roots of the denominator, that all these roots of the denominator, they are in the are negative. So we do have then a decaying exponential instead of a growing exponential. So let's go, well, here I will explain this then in a minute on the credit card balance. Here is the first form of doing feedback. That's to use a constant transfer function. So in the literature, one uses this constant kappa. So this is the gain. So if we have here an unstable plant, so the root of the denominator is 1. So let's look at the transfer function of the closed loop system. So we have the original transfer function, the transfer function of the given plant. We put that in the numerator, and in the denominator we multiply this with this constant kappa. So after some simplification, so if we bring the s minus 1 into the denominator, so from the numerator into the denominator, you see that there is a very simple form of the closed loop function, and the closed loop system will be stable for any kappa that is less than 1. So this looks kind of simple, and it is also simple if you look at the differential equation again, or let's look at let's look at the example of the credit card balance, where we now have two parameters, the initial balance and the interest rate. So in a way, it's not so surprising that your feedback, your proportional feedback, must be proportional in order for this process to stabilize. It must be proportional to the balance and the interest rate. So your kappa should be larger than the interest rate divided by the initial balance. How do we get there? Well, we set up the transfer function of the closed loop system. So we do some simplification, very similar. We bring in the s minus r from the numerator into the denominator, and then we look for the root. Since this is a linear denominator, the root can be seen, and it depends on the original root, so which is the root for the interest rate, and we have the initial balance that's sitting in there as well. So we want that the root is negative, which you can formulate as a condition on the interest rate. But actually we are interested, the interest rate is typically not within our control, and the initial balance, well, that's what we took out of on this credit card, so we can't change this either. What we can change and what we should change is the kappa. Okay, so I leave a numerical example as an exercise. So what happens if you can afford $50 every month on an interest rate 12%, and this is continuous compounding, so you can use the exponential on a balance of 1,000. Will that in the long term reduce the credit balance? Will this lead to a decaying? And you have to set up the transfer function of the closed loop system. So to examine the evolution of the balance, you will look at the solution of the differential equation, where you have the growing balance, and every month you subtract from that balance $50. but then also look at the closed loop system. Okay, now I will end. So this is a lecture scheduled for 50 minutes, but you see I will have enough for 40 minutes. So we still have 4 weeks left. Well, actually, 5 weeks in total in this semester, but the last week is reserved for project presentations. So we have actually 2 weeks, or perhaps less than 2 weeks, to decide on a topic for a last project. So we have already covered. There were already 3 project proposals for on ordinary differential equations. We will have projects on feedback and also projects on the topic that then follows on partial differential equations. So in a way, there is no hurry to make your decision now, but if you were kind of pressed in time for the previous projects, the sooner you start with the topic, the better. Okay, feedback is an important concept, and one can interpret the theories of Adam Smith, the economic theories, the historical economic, one can describe them with feedback. So if one looks at the labor market, then workers that are available on the job market, they will look for employments and consider all various employments, types of employments, and they will naturally they will choose those jobs that offer the greatest rewards. But then the rewards will actually also, in a competing labor market, so the rewards will then also diminish if you have many more workers choosing that type of employment. So that's kind of contradiction, but there is this back and forth process. So there is this action and reaction forces, which can be described by feedback. And you can think about this. Perhaps if you think about it, you already figured it out already. But it's strongly recommended that you read the paper. You will actually see the diagram that is in there. So this paper is, by the way, available via our UIC library. So you can download the online version. So read the paper is actually step 0. So that's something that you can do even to decide whether this is an interesting topic. So I should actually have said right from the beginning that the material here looks very much like into engineering, and if you're not so technologically oriented, this might not be so appealing. But here we see an example that feedback is quite useful to explain various mechanisms. So look at the paper and use your own words and use feedback to define particular feedback as applied to the labor market. We are interested in a particular market and in particular subjects. So this is a course in mathematical computer science. So look into the subjects of mathematics and computer science and what is the labor market there, and you can narrow it down to academia, for which you can look at the supply and demand there. So there are look for data or look for a description applied to the academic labor market, which is, by the way, quite diverse. So there are various kinds of positions, teaching positions, research positions. Also look into mathematics and look into computer science. So that's the first type of project. Then this is a computational course, so we are using Julia and Jupyter throughout. But if you're curious about software, and especially since feedback and control is so important, there are there is software available for this, um, dedicated to control. So Skylab is, I think, the major open source package in this area. Um, what does this package do? And in particular, give kind of an overview why you would need this for control. So you can kind of so throughout the course, we have been working with Julia and combining numerical and symbolic computations and using the visualization, the plotting, and various other packages. Why would you still need a separate software package? So you can also give your overview from the question, why would we need to install Skylab and this other package for doing control? Um, then I hope that the answer is positive. The answer should be positive. The website for the software lists various use cases. Reproduce one of those use cases. So this is a little bit open-ended. Consult with me if you run into difficulties. Um, Report writing is very important in this course. So in some sense, this is a software project. It could be all too easy that you get sidetracked. So in deciding and in any project, you have to present as much time on the presentation, the oral presentation, and the technical report as much as the actual investigation. So keep that still in mind. Okay, so I got the inspiration for the projects from the sources listed here. So there will be more topics coming in later lectures. So we have now 5 project descriptions. So as one surely recommended exercise, please look at all these 5 project proposals and see, do your own research a little bit. Even if you do not are going to pick, say, any of these 2 projects listed here, it could be very good to visit the software website and also to download that paper. We are so the importance, so control is worth an entire course, but at this point in time you should be quite capable to read, say, the first chapter of this Dwarf Bishop book. And we are very close towards the end of chapter 10, so we will still spend 1 lecture on chapter 10 in our textbook before we transition into partial differential equations. Okay, thank you for sitting through this recording. I hope this lecture was interesting, and we will return for 1 more lecture on the frequency domain methods. Summing up for today, we stated, proved, and illustrated the application of the continuous version of the theorem on the Bode plots that we covered earlier in the course. We introduced feedback with the credit card example. We will cover more examples in the next lecture of feedback.